Hello, this is lecture 5-stat135. You're going to have a quiz on Friday consisting of 3 problems. 2 problems will be similar to problems from homework 1 and 2, and there'll be 1 mom calculation. Last time we did method of moments and consistency. Today we're going to do a mom calculation, look at non-parametric bootstrapping of CIs, and also the standard error of the sampling distribution by hand. So here, number 16a, chapter 8, is an example of a mom calculation. We review the gamma distribution. The density of the gamma distribution has a variable part involving x. The integral of the density is 1, and that gives us, this leads to this important identity that we'll use below. So consider an IID sample of random variables with density or likelihood given by this formula. Find the mom estimate of sigma hat of sigma. Find the mom estimate sigma hat of sigma, yes. So step 1 is we find a moment. There's just a single parameter, so there's just one moment we need to calculate. However, we see that the first moment is 0, and that's not good for us because the moment needs to be a function of the parameter. So that leads us to need to calculate the second moment. Doing this and utilizing the fact that the variable part using the fact that the integrand is the variable part of gamma, 1 over sigma, we find the second moment to be 2 sigma squared. We then write sigma as a function of our second moment, and finally find the method of moment by substituting the sample moment. So, non-parametric bootstrapping and confidence intervals of a population parameter. This is material from section 8.5, but I'm doing it now because you have a lab today, and I want you guys to practice this in R. So, just recall that to calculate a 95% CI of the population mean by hand, you need simple random samples so that we can find the variance of x bar, which we have a formula for, and the sampling distribution has to be normal so we can find the 2.5 and 97.5 quantile of x bar. So this is very restrictive. Often the sampling distribution isn't normal, and perhaps we don't have an SRS. So instead, we're going to find the 95% CI by bootstrapping in R without making any assumptions at all. First, a little theory about confidence intervals for a general population parameter. So let theta be a parameter of your population, and theta hat be an estimator of theta, could be a mom estimator. And we're going to look at theta hat minus theta, which is a random variable, not necessarily normal. Suppose we know what this distribution looks like. We could find A and B, the 2.5 and 97.5 quantiles. Then, by definition, the probability that theta hat minus theta is between A and B would be 95%. Some simple algebra leads us to the definition of a 95% CI of theta to be the probability that our population parameter lies between theta hat minus B and theta hat minus A, and it is 95%. So in other words, a 95% CI is the interval theta hat minus B, comma theta hat minus A. Now the distribution for theta hat minus theta isn't known to us. It's only known to Tyche, the goddess of fortune, and so the best we can do is approximate A and B. So that's what we're going to do using R and bootstrapping. So there's a procedure here. Step 1 is we take a one-time sample from our population. Step 2 is we're going to resample this sample 1,000 times and compute the estimator for each of those samples. So call that theta 1 star up to theta 1,000 star. You may be wondering why it's okay to resample from your sample. Well, there's actually theory supporting this. So of course, just in the upshot is that the sample resembles the population, but more theoretically, the population has a certain distribution with a CDF-F, and our sample also has a distribution. It's called the empirical distribution with a CDF that's called the empirical CDF. You can read about that in Rice on page 378. But by definition, the empirical CDF, which we write as F sub n, for a given x, it is 1 over n times the number of data points that are less than x. Just as an example, if you just have 3 data points, 1, 2, and 3, and you wanted to compute, say, the empirical CDF for 2.5, you would see that 2 of my data points are less than 2.5, and so I would get the value 1/3, because there's 3 data points, times 2. So F, the CDF of F is given in purple here, and the empirical CDF is an estimator of F. In fact, it's an unbiased estimator, and its variance goes to 0 as n goes to infinity. You can read about this in section 10.2. So step 3, we subtract theta hat from the theta star i's, and that gives us a list of 1,000 numbers. Now, step 4, we find the 25th and 975th largest value of that 1,000 numbers. And finally, we form our 95% CI, which is theta hat minus B, comma theta hat minus A, where A is the 25th largest number in our list, and B is the 975th largest number in our list. So you'll be practicing that today. Now, if you don't want to use R, sometimes we know analytically what the SE of theta hat is. So I won't say, even if we know the distribution of theta hat, it's often difficult to find the quantiles. So we usually won't compute the confidence interval, but rather we can just calculate the SE, and that gives us some notion of the variability of our estimator. So here we are back in section 8.4. Theta is a parameter determining the distribution of x. SD of x we denote by sigma, which is a continuous function of theta. So for example, if x is Poisson lambda, sigma of lambda is the square root of lambda, a continuous function of lambda. Our estimator is consistent, so that means that sigma of our estimator converges in probability to sigma of theta. So for large n, the unknown sigma of theta can be approximated by sigma of theta hat. So in other words, to find the variance of theta hat, we're ultimately going to need to know theta, which we can approximate by theta hat. Okie doke. So here's just a concrete example. An IID sample is taken, and you collect 5 data points, 4, 7, 4, 2, 3, which follows a Poisson lambda distribution. Find a mom estimate of lambda and approximate the SE of your estimate. So we know that a mom estimate for lambda is the sample mean, which is 4, and we can calculate the SE of lambda of our estimator. It's the square root of the variance of our estimator. In other words, the square root of the variance of x bar, which is the square root of the variance of x over n. Now, the variance of x we can approximate 2 ways. One is if you use the fact that x is Poisson, then you know that the variance of x is lambda, and you can approximate lambda as the sample mean, which is 4, giving us the square root of 4 over 5. Or you could approximate the variance of x as the sample mean, the sample variance, which is a little bit of a calculation, but it turns out to be 14 over 4, which is close to 4. Have a great weekend, guys.